When the ancient Greek astronomers, so Copernicus, Tycho Brahe, all of those men that we learned about at the beginning of the semester, when they looked into the night sky, they saw light coming from our moon and other stars. By studying the night sky, they were able to draw conclusions about the structure of our universe. Well, almost everything we currently know about the universe comes from studying light that stars emit and from light that is reflected from planets and other moons. But today's scientists, they use a variety of instruments to study that light and analyze it because our human eye, our eyes, we can't see it, so we have to use tools to help us. Let me explain in further detail. Okay, stars and other bodies in space emit light that can be used to study them. Although visible light, so colored light, is most familiar to us, this makes up only a small part of the different types of energy known as electromagnetic radiation. So let me write that down. Electromagnetic radiation. I'm sure you guys are going, what is that? See, I can't even say it. Electromagnetic radiation is pretty much just energy. Energy, smiley face. And there are different types of electromagnetic radiation or energy. There are gamma rays. There are X-rays. Everybody's familiar with X-rays. If you've ever gone to the doctor for a broken bone, you've had an X-ray done. If you've gone to the dentist, they take X-rays of your teeth. There is ultraviolet. Ultraviolet is what causes sunburns. Then we have visible light, so color, things that we see. Then there's infrared, which is related to heat. So for all of you who play Call of Duty and use those heat goggles, that's what that is. There's microwaves. And last but not least, radio waves. Okay, and if I was to give you a little chart, which I will use this a little bit later, here's another diagram of them. Gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. Now, I'm just going to move this to the side. All energy, let me write this down. All energy, regardless of wavelength. So when we look at this picture here, really tight or really long, regardless of wavelength. Let me write that down. Regardless of wavelength. So if it's a longer wave, so longer or shorter, all energy, regardless of wavelength, travels through a vacuum, so space, travels through a vacuum of space. So no gravity, pretty much. All energy, regardless of wavelength, travels through a vacuum of space at 300,000 kilometers per second. Or in scientific notation, that is also 3.0 times 10 to the 5 kilometers per second. Well, what does that mean? Let me give you guys a little bit more explanation. And I have a copy of an electromagnetic spectrum. And the electromagnetic spectrum contains the different types of radiation I just mentioned. Let me grab a pen. A pen might be a little bit easier to see and work with. Ooh, let's go with blue. have a blue pen handy? I do. All right, I have a blue pen. Let's put something to write on. Flip that over. There we go. Let's label our electromagnetic spectrum. You guys do need to know this. This is super important. Like, this will be on your next exam. Let me write this down. Will be on your exam. You got to know this. So what you see here are a bunch of different boxes, and we have a wave here. And the wave, as you can see, it's getting longer, and through, as we move across in distance here, the wave appears to be getting tighter. And the distance between each wave is tighter and tighter and tighter, so this wave frequency is actually increasing. So I'm going to write it over here. It's increasing. And the wavelength is getting shorter. Okay, so that means the opposite. Over here, it's getting longer. And the frequency is decreasing. So frequency is energy, and wavelength is going to be the distance between each wave. All right? So there's different types of radiation I'm going to fill out on this chart for you. So we'll start in the right corner. We have gamma rays, which are these guys here. I'll do this at the end. We have gamma rays, then we have X-rays, ultraviolet light, so I'm going to put UV, ultraviolet light. Then we have infrared, microwaves, and radio waves. Okay. Radio waves have the longest wavelength and the lowest frequency. And as we move to the right, wavelength starts increasing, frequency starts increasing. Now, visible light, the reason that visible light is brought up or extended out of this chart is because this is something we can see, and we can't see the others with our own eye. And there are different colors that go with this. So red light is going to have a longer wavelength. I'm not the best at coloring, so the girls who are really into coloring, leave me alone. I don't color in the lines. Red is going to have the longest wavelength as far as color is concerned. Then we have orange. Then we have yellow. Then we have our green. I'm sure the girls are definitely spazzing out. I don't color in the lines, it's okay. Then we have our blue. And last but not least, we have our violet, or purple, purple violet, blue indigo, same thing. And when we talk about these colors, you will often hear them say something like Roy G. Biv. Something like that. It's to help you remember the colors. Red, orange, yellow, green, blue, violet. And to get a sense of how long and short these are, let's talk about what unit this is. These are all going to be in nanometers. Nanometers are extremely small, like really, really small. Of course we can't see them, but extremely small. And if I was to give you a breakdown of the wavelengths, our red would have anywhere from 750 to 640 nanometers. Then it would go 640 to 590, and then yellow would go 590 to about 560, and then green would go 560 to about 500, and then blue would go 500 to about 440, and then our violet would go 440 to about 380 nanometers, just in visible light. Radio waves, microwaves, somewhere in between here, is about 30,000 nanometers. Between microwaves and infrared is about 1,000 nanometers. So we're getting really big, then we're getting smaller, then we're getting smaller, and then between our ultraviolet and our X-rays is about 10 nanometers, and gamma rays would be about 0.01 nanometers. And that is a pretty good explanation of our electromagnetic spectrum and the different types of energy. And then just for visual representation, I'm going to cover up the wavelength. You have your X-rays, your gamma rays, ultraviolet, radio, microwaves, infrared, and visible light, what we can see. There is your electromagnetic spectrum explanation. But Mr. Large, I still don't understand visible spectrum. I don't get it. Can you show it to me? Yes, I'd be more than happy to show it to you. Give me just a second. Here I am in my awesome classroom with no kids, and I've got a pair of very flimsy glasses here. You can kind of see the different colors, the spectrum. It's not a rainbow, it's called spectrum. Not a rainbow, spectrum. And I'm going to show you that visible light that I explained. So when we look at our light bulbs, ew, not this one. Let's pick this one here. When we look at our light bulbs, if I take these flimsy glasses, I'm going to do it long ways, you can actually see the visible spectrum. Watch. I'm going to put the glasses over my camera lens and look at that. That is the visible spectrum that I just explained earlier in this video. If I move my glasses, that's what we normally see. But when I put this diffraction gradient up, you can see the visible light. Now, oh, isn't that cool? But Mr. Large, that's only coming from the light bulbs. How do I know that that's real? Well, let me show you. I'm gonna walk outside. I have my keys? Yeah, I have my keys. Okay, so here's our beautiful campus at Granite. And it's bright, and it's sunny, and it's beautiful. And I'm gonna do the same thing. I'm gonna take these glasses, and I'm gonna put them over my lens. And look, you get the same effect. If I move the diffraction gradient, you don't see the spectrum. But if I put it back over, you can definitely see it.